Okay, so hello everyone. I'm Baptiste Vergain. I'm working with Bernard Boigelot and Pascal Fontaine on my PhD currently, and today I'm going to present the work that we are currently working on arithmetic with unary predicates for SMT. So first, well, bear in mind that this is still a work in progress. So we have some results that we're quite confident on, but some that we'll present later on are still not completely clear for us. So we also welcome any advice or ideas after my presentation. So the context of the research is as a satisfiability modulo theory. And we decided to look at logics that are placed at the frontier of decidability. So trying to, yes, get the ones where if you add anything, any more expressive power, you'll reach undecidability straight away. And our final goal is to get, for such logics, an effective decision procedure. So the logic that we decided to target, we wanted to have two aspects and play with both. We wanted to combine arithmetic and uninterpreted symbols. But we know that with that, there's some fundamental decidability limits with that. So first, purely from the arithmetic point of view, we know that there is a point around here where there are some already without any uninterpreted symbols, we reach undecidability. For instance, around there's piano arithmetic. And for maybe decidable arithmetics like Pressburger, so the first order logic of on integers with addition, we know that adding even a single unary predicates make us reach undecidability. Okay, and on the other hand, if we look at uninterpreted symbols, we know that it suffices to have three binary predicates to reach undecidability without any arithmetic. And so the idea is to remain beyond decidability and to reach for a logic that allows unary predicates, if possible, without any restriction on them, and that has some arithmetic that is interesting to work with. And for that, we decided to elect a reasonable candidate, which is difference logic with unary predicates that are present now. Okay, so the logic we targeted is a first order logic on a fixed domain D, which is intended to be the naturals, integers, or even the reals. The arithmetic atoms, so are difference logic atoms. So basically we have states that we have two variables from our domain D and a constant from the same domain. And we have a relation that states that X and Y, basically these atoms just states that you can order X and Y, one is before or after the other, and you can give more information about the space that separates them. Either it is exactly equal to something or greater or lesser than a constant. We also allow variable quantification, so universal and existential, and the usual logical operators. And to that, we add the unary predicates for any number of unary predicates. So first, let's see a few examples of what we can express with this logic without considering the domain yet. But for instance, we can consider a formula that describes the predicate parity if it is interpreted on the integers. So it is indeed parity since this predicate is true in 0, false in 1, and for any two integers, if their difference is exactly equals to 2, then either both are even or both are odds. Another one, which seems a bit more complicated, is density, specifically of the predicate here. So it just means that the formula translates to if you take any two elements of your domain, you can find one in between which satisfies the predicate. Okay, so it's really the idea of the predicate being dense in the whole domain. And another one which we call chaos, which directly derive from density, translates into this formula, which means that if you take any two elements of your domain, in between you'll find both a value that will satisfy the predicate and one that will not satisfy it. So basically, chaos means that the predicate and its complement are both dense on the domain. Okay, so we see that we can start to express some things that are already quite interesting with this logic. And now let's see about the decidability of this logic on the naturals first. Actually, in the naturals, it's rather simple in the way that this logic is equivalent to S1S, so the monadic second order logic with successor. And that can be proven since they have the same expressiveness as Buki automata. So I'll give a few details on the proof. I only focus on the first part here, the transformation from formulas to automata, and not on the second one. But the idea is that we don't directly work with S1S, but only with a transformation from all overall logic formulas to Buki automaton and reciprocal. Okay, so to transform formulas from a logic to automata, the first issue is to find a way to encode our variables and our predicates. And we can do that rather easily with omega words. And since we have omega words, we are actually in need to define corresponding Buki automaton from a given formula and make them work together. So I'll go into more details on the next slide. And the transformation from automata to formulas is actually rather classical since the logic allows us to work with any number of predicates. Encoding a Buki automaton state in transition in our logic ends up being rather easy because transition and states can be easily encoded with a lot of predicates. Okay, so just so for a few more details on the transformation from formulas to automata. So for the first part, the encoding of variables and predicates is kind of straightforward. For a variable, for instance, free, you see that you have an omega words, and the only value where there is a one is it's at the index of the value of the variable. And for a predicate here, for instance, the predicate even, see that at the index 0, the predicate is true, it's false in 1, true in 2, false in 3, and so on. So it's quite easy to work with. And in order to transform the formulas to automata, first work with the atoms of our logic. So I'll only consider these two to show you how it works. So for the atom that states that the predicate P is true on the variable X, you have a Buki automaton that reads two omega words that describe first the predicate P and X. And we see here that at first, X is not yet met and P can be whatever you want. And once we reach X, P has to be true at the same point. And then P is again free and X must only contain zeros afterwards. And for the difference logic atoms, basically this states that, so the X is so much greater than Y that we at least reach C cycles. So we first meet Y, then we know that we take at least C steps in our automaton before we reach X, and we know that the space between the two variables is great enough to satisfy the atom. Okay, and once we have actually transformed these atoms to automata, what we need to do is to deal with the Boolean combinations of those atoms to construct any formula from our logic. And so we can only consider those operators, since combining them allows to use every Boolean operators. So for the conjunction, it results only in an automaton product. For the existential quantification, we just have to do an automaton projection on the variable that is projected, that is quantified, sorry. And for the negation, we just need to use the complementation of the Bookie automaton, which is known and works well. Okay, so this is just a few details for the proof on why all logic is decidable on N, on the natural, sorry. So we have decision procedure for the naturals, and now let's see about other domains. So first we'll see for the integers entirely. The extension to the integers is quite easy. There is no real increase in the expressiveness, since you see that the encoding is quite similar. We just use the usual bijection from the integers to the naturals. You can see it here. And for the variables, it's basically the same encoding with only one place where there can be a 1, which is the corresponding value of the variable. And predicates, there is a 1 each time the predicate is true for the matching value. And the resulting automata that you get, they are still Bookie automatons, so it works exactly in the same way. They have the similar shape and they're just slightly bigger because you have to deal with the alternation that we used here. Okay, so this is not something really new, or it's already quite known. Where it gets really interesting is when we get to the reals. First, you can see that it is significantly different from the naturals because, for instance, if you take this this sentence in theory, the sentence is false for the naturals, but it's true for the reals, as this one describes the density of the whole domain. So it looks a lot like the density of the predicate that I showed you beforehand, but there's no predicate involved here. So it just says that for any two elements of our domain, there is one in between. And the problem is that when we reach the reals, we cannot use the same encoding for variables and predicates as before, because especially for the predicates, there is an issue with the fact that we need the information on way too many elements for coding in on a simple omega words. So we need another representation. And what we do for that is to focus on how the predicates behave on a given interval. Okay, so first for this part, let's notice that we limit ourselves to only one predicate yet, and we don't even consider pure difference logic atoms. So this is really a restricted version of a logic because we're not even completely sure yet that it works perfectly. So we still focusing on a simplified version anyway. So for a given predicate on a given interval, there are basically three atomic behavior. You can see either the predicate is uniformly true on the interval, or it is uniformly false, or we get what we presented as chaos beforehand. Basically, the predicate and its negation are both dense on the interval, and there is no subinterval where we meet either of these atomic behavior. So now that we have some atomic behavior, let's see how we can mix things up and make it a bit more complicated. And for instance, let's look at so this big formula that looks a bit ugly at first, but it's actually not that complicated. So it just states that there is a point on our domain where first the predicate is false at its place. So this figure represents that. So basically here is the y of the formula. Then it states that at the left of this value, the predicate is uniformly true. Okay, so we get one of our atomic behavior on the left. And on the right, we get another one, which is the chaos that I presented beforehand, which is there and on the right of this value. Okay, so basically what we've done here, even though it's not necessarily obvious when you look at the formula, is just that we concatenated two atomic behavior while specifying how the predicate behaves at the junction of the two intervals. So on top of that, we can consider what other combinations are possible. So we made the concatenation, but there are actually many more, but that are quite natural. So first there is a union. So basically it will correspond to the disjunction of two formula. A predicate satisfies either one of the two behavior, B1 or B2. From the concatenation and the union, you get the usual idea of the clean closure. So basically it's any finite concatenation of a certain behavior. And we also specify how the predicate behaves on the junction at each time. And more importantly, we also get what we call right and left convergence, that I will illustrate with an example right now. And so basically it's the idea of the limit of the clean closure when we get an infinite number of concatenation. And so let's illustrate that with an example. So for instance, if we get what we had before, so true concatenated with chaos and false at the junction, if we put that, if we get the right convergence of this whole behavior and we concatenated to false, so we get an infinite number of times this behavior, there, and it converged to a certain point, and then we reach this specific junction that is here, and then it is false up to infinity for any number greater. Okay, so you see that you can start to create things that are a bit more complicated, and of course you can combine all these operators between themselves to create things as complicated as you want, but within the realms of these operators. And as you see, what we've actually managed to do is to present, to describe the set of predicates that satisfy the formula into a regular expression. And the real idea behind that is to get, is to obtain an interesting automaton that deals with such regular expression, and is able to, and that we are able to work with to decide the language. Okay, so I went a bit fast there, I guess. Okay, so in conclusion, so what we've already done, and it's work in progress, is we actually, I think we have a clear view on how it works, on how our logic works for the naturals and the integers. Even if we add numerous predicates, the only lead that we could pursue on that, but it's not our main focus yet, is to perhaps work on quantifying those predicates. We don't exactly know how our logic would evolve from that. But currently our main focus is on working with the reals, so with this reduced logic. So what we want to know is specifically if the representation that we just presented you is complete for the expressiveness of our logic, and especially if it's scaled well when we add other predicates and when we consider true difference logic atoms. And on the other hand, to find or create the proper automaton that will deal with the regular expression that we presented. And we already have some leads that will deal with especially linear orderings, but I will not go into more details on that yet. And later on, if that works well, yeah, we want to get a clear idea of the logic, the expressiveness of logic out of the reals, and possibly get an effective decision procedure for that as well. And we're also aware that there are some very similar logic that exists. Specifically, I have in mind one is called the form law, and that we have to investigate to be sure of where our work placed itself with the state of the art. But we are quite confident that with our automaton approach, even if there are some results already exist, we have a new perspective and something new to bring to the state of the art. So thank you for your attention, for listening. If you have any question.
Thank you very much, Pascal. So we do have some time for questions. Baptiste, pardon.
No problem.
We do have some time for questions. Martin has one.
Hi, can I ask two questions? One of them is the awful, do you have examples of things that are in this subset? And the second one is, how would you, is it possible to implement this in a way that works with existing handling of quantifiers?
So if you want me to answer,
Yeah, perhaps Pascal will be.
well, but if you want to,
I'm not sure.
okay. Yeah, well, about examples, we are not guided by examples here, but we would like to work at the frontiers, as Baptiste said. We would like to work at the frontiers of decidability, and that's why we are studying this this fragment. So we don't especially have well, industrial applications for this. But the idea is that we would like to understand more this fragment in order to be better also outside of the fragment. So that's a bit the idea. And also, I mean, it relates to the second question. Indeed, I mean, if we develop techniques that work on automata, they will be quite specific to automata, but we hope to be able to translate those techniques into something which is more formula focused, so that we could apply it in a larger framework. So yeah, I hope this answers your question.
It's a far better answer than my unhelpful and awful questions deserve, certainly. I think the link with quantifiers, that would be fascinating, like, because, you know, is it that you can use the automata you're creating to do quantifier instantiation by, you know, following the automata in some way? If that was the case, that would sort of generalize some of the stuff on ordering of instantiations, and maybe, you know, actually give a theoretical basis for sort of people talking about quantification loops and instantiation loops.
Mm-hmm.
And that then starts to sound incredibly applicable.
So if you Martin, if you have links, I would be happy to have them. So something that we should read. Don't hesitate to send them to. I mean, even if it's some vague direction for research, I would be happy to have
Okay, I will send you a suitably vague and unhelpful email.
Okay.
Thanks.
Thank you.
No, Martin, I doubt that. Are there any other questions? We have a few minutes.
Not a question for me, but just a comment to say, very nice work. That's beautiful.
Oh.
Thanks.
Thanks, Grant. Yes, indeed. It's interesting that I expected when the talk started that we'd see that it worked for N and Z cause problems, but it's interesting to see that R, it's between Z and R. You haven't actually mentioned, that's a good point, here's a question. You haven't actually mentioned Q, the rational numbers as such. Because you have problem, sorry?
Yeah, I haven't mentioned it yet. We're not quite sure of how it behaves. We think that there is not necessarily a lot of difference with the reals, because we haven't found yet in a way to discriminate between rationals and reals with our predicates and our formulas. So we think that it would be the same as for the reals, but
and we do have a bit of hints for proof of that any formula that is true in one is also true in the other, on the other domain.
And at least if you're in the linear fragment of the language of ordered rings, the true theories of both should be the same, right?
Mhm.
Because it's the linear fragment. So you can't build root 2 in a linear fragment. Is that the?
That's the idea,
Yeah.
yes. Yeah.
Yeah, you can't. Basically, they at least should be equisatisfiable if it's linear.
Mm.
So I think.
Yeah, well, we have some kind of hand waving proofs that we can translate a model on R into a model of Q, and well, vice versa. But it needs more work. It's work in progress.
Okay, that's interesting. But thanks, Grant, for that very helpful intervention. Any other questions?